This is the fifth and final section on neutral molecular evolution for preparing for class. And what we're going to do is talk about some of the counter arguments that came up after Kimura came up with his ideas for neutral evolution being so important. So, as you might imagine, lots of people did not immediately agree with Kimura, and they started to think about why his ideas and theories might be incorrect. And so we'll talk about three of the reasons that they thought he might not be entirely correct. The first one is he had assumed that all death in a population was due to what we call hard selection. And he also assumed that each locus acts independently on fitness. We talked about this in the previous set of videos. And we also talked about the fact that he thought, and many people did, he wasn't alone, that heterozygous advantage was the reason that populations would maintain variation over time. So the counter arguments are simply that natural selection is soft rather than hard. I will explain what that means in some detail. Hard selection basically means that all of the death or loss of reproductive capacity from selection is in addition to something we call background mortality. Soft selection says that the selective deaths are actually substituted for the background mortality. And I realize that may not be clear, but I have some illustrations in a minute that will help you understand this. The importance of this is that soft selection reduces the cost of selection that we've talked about previously. And the reason is no additional deaths occur in the population above the background mortality. So selection is not imposing an additional reproductive burden on the population. And Kimura and Haldane had assumed when they talked about the way the cost of selection would work, that selection would be hard selection, not soft. All right, so what do we mean by this so that we can make sense of it? Let's start by understanding what we mean by background mortality. So what we have over here on the left is a population at birth. So the total population size is 120. We have 30 individuals that are homozygous, large A, 60 individuals that are heterozygous, and 30 individuals that are homozygous, little a. And that's what things look like at birth before anything has happened. Now, to understand the notion of background mortality, we have to think ecologically. And that is, we know that all organisms can produce more offspring than the environment can actually support. And so even if there's no selection taking place, that is, if every genotype experiences the same proportion of death before they reach adulthood, that's going to occur not because of natural selection. It's simply going to occur because there's not enough food or other resources to go around. And so some individuals will simply die because of that lack of sufficient resources. So in this case, with pure background mortality, we're going to say that 50% of the individuals in every single genotype are going to die off by the time they reach adulthood. And so that's being shown here. Those are the hatched areas that I've added here are the deaths. And so 50% of the individuals are dying off before they reach adulthood, leaving in this case 15, 30, and 15 in each of the genotypes. And if you look proportionately, the genotypes are in the exact same proportions that they were to begin with, 25, 50, and 25 as proportions. So there's been death in this population, but no selection has taken place. And then if that population is stable, the same thing happens in every generation. Okay, so we just get a repeat of that, and it's just pure background mortality taking place in every generation. Now let's look at what hard selection looks like. Here on the right-hand side, I've put a chart of what the background mortality looks like just to remind you what it, and so we can compare it against the hard selection. So over here, we've got the same population at birth. We're going to impose the background mortality, so 50% of the individuals are going to die off just because of a lack of resources. And then under hard selection, the additional death that takes place is above and beyond that background mortality. And so that's what I've symbolized here with this other type of hatch marking here in the blue and red hatches. And those are the selective deaths, and I put them in the homozygotes because we're talking about heterozygous advantage. So the issue here is that originally, if we look over at background mortality, the population had to have 50% excess reproductive capacity so that it could produce 30, 60, and 30 individuals at birth, and then have this many individuals come through for the adulthood. Here what's going to happen is, because of the additional death that takes place here, instead of having 15, 30, and 50, the way I set up the selection here, we're going to have 7, 30, and 7. And so the population size is now smaller, and the remaining individuals have to have enough excess reproductive capacity to not only replace all the individuals that died because of the background mortality, they also have to replace all the individuals that died because of the hard selection that took place against them. And if the population doesn't have enough excess reproductive capacity above and beyond the background mortality to do that, then the population will get smaller in every generation and eventually go extinct. That was the basic idea behind Kimura and Haldane's notions of the cost of selection. So that's hard selection. Now, under soft selection, something different takes place. Again, over here on the right, we have background mortality as a point of comparison. And over here, we have the same population at birth with 30, 60, and 30 individuals in the different genotypes. Here what happens is the total amount of death is exactly the same as it would have been with background mortality. It's just that we redistribute the background mortality so that the genotype that's selectively favored has less of the background mortality than does the types that don't. So that when we reach adulthood in this population, there's still 7 individuals here that died off in the homozygous types, but 46 individuals are going to survive now in the heterozygous condition. And if you add that up, 7 plus 7 is 14, 14 and 46 is 60. There are 60 individuals in this population, and there are 60 individuals in this population. So there is no need for excess reproductive capacity in here. Selection has taken place because there was differential mortality between the homozygous types and the heterozygous types, proportionately. But because a total of 60 individuals made it here, they still only have to be able to produce twice as many offspring as themselves to get back up to 120 for the next generation. And so if you have pure soft selection, there is no cost of selection above and beyond background mortality. And if that's true, if you have pure soft selection or something that's approaching pure soft selection, then the cost of selection becomes much, much weaker, and the population can tolerate a lot more death in the genotypes that are going to be selected against. All right, so hopefully that helps. Then the second thing we talked about was the assumption that all the loci act independently. Remember, we raised that number of the average fitness of the population to the 3,000th power because we assumed that all 3,000 heterozygous loci were acting independently. But we know that that's not true. We don't fully understand exactly how the genome interacts, but we do know that there are redundancies in the way different pathways work, different biosynthetic pathways. Now here, when you have a non-redundant network where A will produce B because of enzyme X or vice versa, this is a one-way street, and if this enzyme goes away, we can no longer get B from A, and so that will act independently. But as soon as you set up any kind of redundancy in the network, that's not true. Here we still have A and B can be produced by enzyme X. But if enzyme X mutates and becomes non-functional, we can still get to B because of this alternate way of getting there. The enzyme Y makes C, and enzyme Z makes B from C. And so just because this type becomes less advantageous, it doesn't necessarily mean that B won't be produced in adequate amounts. And so what that means, basically, is that instead of raising that equation to the 3,000th power, depending on how redundant the networks are, you might only have to raise it to the 1,500th power or maybe only to the 200th power. Nobody knows exactly. But that would reduce the effect of all of those loci being maintained by heterozygous advantage. Now, whether it would reduce it enough to fundamentally change Kimura's argument is open to question, but it would nonetheless reduce the overall effect on the average fitness, and therefore the reproductive capacity wouldn't have to be quite so great in the females that do make it to adulthood. The other types of selection that could be maintaining variation. At the time that Kimura was doing his work, it was thought by most of the community that heterozygous advantage would be the main way that variation would be maintained in populations. And so it was true that if you had heterozygous advantage and hard selection, you would in fact have a cost of selection in every generation that would just never go away. However, there are other forms of selection that people have worked on since then, understanding since then, that will maintain variation in the population without the same kind of cost. So for example, frequency-dependent selection, which we haven't talked about in any detail, but this other form of selection will maintain variation in a population, but without the kind of costs of selection that you have in maintaining variation with heterozygous advantage. And so again, this lowers the cost of selection and makes it possible for there to be more variation in a population than Kimura had originally thought would be possible. So given these counter-arguments and what we've learned since the late 1960s, early 1970s, what should we think about this? Well, the first thing is that now it appears that either neutral evolution or selection could account for many of the patterns that we observe. And from experiments that have been done, we know that there's just simply not a simple answer to this question. We've talked about this in this class already. We know that different regions of proteins and different proteins are under different levels of selection, and they can tolerate more variation. And so, depending on the protein or the region that you're looking at, it may be evolving neutrally, or it may be under very strong selection. And some loci are almost certainly more nearly neutral, and others are going to be affected by selection. So it's not all one thing or the other. Kimura was right in the sense that, yes, there is neutral evolution taking place, and certainly more than people thought about in the late 1960s. But it's not all neutral evolution, or nearly all neutral evolution, the way that he was originally talking about it. Okay. Now, it probably doesn't surprise you to hear any of this, but you're looking at this from the perspective of somebody living in 2013 versus somebody living in 1968. So you have the advantage of hindsight, so don't feel too superior to the people who were thinking about the problems back then.